All right, hey class. I'm gonna give you a overview of beam analysis today. So we're going to share my screen here first. We're gonna look at beam analysis. Got a little quote here. We're kind of building two kinds of goodness. First, the doing their practical duty well, and the graceful and pleasing in doing it. So we're really looking at, hey, we gotta make sure structures are sturdy, and then we can look at all the fun stuff, aesthetics or things like that. So. Without further ado, I'm going to jump right into it. So first off, when we talk about beams, these are structural members that carry a load that's applied transverse to its length. So meaning that if the length is this way, transverse coming down along it. Oftentimes used in floors and roofs, and sometimes you hear them as floor joists, stringers, floor beams, or girders. Last class, we looked at tracing or chasing the load. And so that's kind of following a given load or a force and kind of seeing how does it move through the structure until it reaches the ground or the soil. So in this case, loads are initially applied to the surface of a building. So in this case, the floor, or maybe it's a roof. And those loads go from the beams down along here to the girders, down until it hits the columns, into the footing, until it hits the soil. All right, so this idea of static equilibrium, today is actually going to feel a little bit like a physics class. So for those guys that have taken physics, some of these terms might sound familiar. For those of you guys that haven't, this will kind of be an intro to some physics concepts. So the first one here is static equilibrium, which essentially means when all of your forces balance out so that the object is not moving, aka stationary. So in order for something to be static equilibrium, I should say this way, you want your beam to be in static equilibrium so that it will carry the loads without actually moving around too much. So obviously you don't want buildings moving to a point where they break. So in this case, we got the loads that are applied to the beam. So this from the roof or from the floor, and they must be resisted by the beam support. So the forces will be referred to as a reactionary force. So for every action, so for every force, there's always a reactionary force in between two objects. And so in this case, we see the applied load coming down. The reaction forces will come from the columns or maybe from the beams, depending on which way you're looking at it. Also, this term vectors, you should be familiar with if you've taken any physics or maybe even some math classes. So vector is referring to a value that has both magnitude, so meaning it has a size and it has a direction. Okay, so forces are vectors, and so they have both magnitude and direction. So the direction is important, and it's something that we will want to keep track of. All right, so in this moving forward, we have reactionary forces. They can be both linear or rotational. So a linear reaction force is often referred to as a shear force. So you'll see that marked off as an F or possibly an R. The rotationary force is referred to as torque in your physics classes. When we talk about this in structural analysis, this would be a moment or a moment reaction. And we're going to mark those off with an M. So reactionary forces must balance the applied forces in order for you to have static equilibrium. All right, next up, we'll talk about some different beam supports. So this is kind of how the support actually works, so that how it's going to actually balance out the forces. So if you have a roller, as shown here, that means you're just being supported upwards. Okay, so if you, place a beam along a non-fixed point, that would be a roller. Next up, you have a pin connection. You can almost think about this as a hinge. So a pin connection is able to support it upwards. Also, it has that horizontal force. So you have the Fx as well as an Fy up. Next up, we have a fixed support. And so the fixed support will have the up and the down, and it will also be able to have that reactionary moment force. Okay, here's a couple other ways of talking about that. So a simple beam would have kind of this pin connection on one end, and then have a roller on the other. If you have a continuous, that's where we have pin on one side, and then multiple rollers. And then a cantilever is just fixed on one end, and that's how we account for that moment. All right, you can also have a fixed beam altogether. That'd be fixed at both sides. Hence, there'll be moments at each end. We'll also have a propped, so it'd be fixed on one side and just supported with a roller on that side. and an overhang where the roller is kind of somewhere else along the beam rather than at its end. Okay, so here's a simple beam. We have your applied load coming down and your reactionary forces. In this case, since we have a pin on this side, we technically have a horizontal force as well, but oftentimes we'll ignore that horizontal reactionary force unless there is some sort of applied force coming in horizontally. So for example, if there's some sort of a wind force coming through, then we might have to account for that. But for our class, we'll typically just keep it a little simple. Our forces will be going straight down, so our reactionary forces will be up, and then we'll just also have to account for the moments. All right, so the fundamental principles of equilibrium is, again, we want all of our forces and all of our moments to sum to 0. So here we have our sum of forces. The sum of all vertical forces should come out to 0. The sum of all your x forces should go to 0, and the sum of all your moments should equal 0. We want that to happen because if it's not, that means there's going to be unbalanced force, and that oftentimes is where we'll start seeing structural failures. Okay, so a little bit more about what a moment actually is and how to calculate it. So a moment happens when there's a force that's causing rotation. And how this happens is if you have a force that's applied at a perpendicular distance compared to a fulcrum, or in this case, kind of a point of rotation. And so if that happens, then you end up creating a moment. So a common analogy I would use here, or an example, would be a door, right? So a door has a hinge or a pin on one end, and then the other side, typically when we open the door, we're applying a force of either pushing or pulling to open the door, and it's a certain distance away from the hinge. Okay, so imagine if you tried to open a door right at the hinge, it would be impossible. You'd just be pushing on the hinge and the door wouldn't open. So you need to have a distance away from that pivot point or that hinge in order for you to create a moment, or meaning a rotational force. So here we have, again, imagine a door. You have to push it a certain distance away from the hinge or away from the pivot, and in order for you to create rotation. All right, so let's get into the math. Like I said, this will feel a little bit like a physics class for a little bit, but I'll try to walk you guys through this step by step. Okay, so first off, we'll sketch a beam diagram. So some of the common ways we'll draw this. Over here, we have our pin. We use a triangle. The line with the little dashes along it is representing to be fixed. So this would be like to the ground. Over here, we've got a roller. So we use a circle. And then again, line with the dashes on it represents it being fixed. Okay, besides that, we keep track of some dimensions. So in this case, it's showing that if this force is being applied 6 feet from point A, over here, we see it's 14 feet from the B side. And in total, the total beam is 20 feet long. Okay, the other couple notations here, the P force, this would be a point load. And so it's only being applied at one spot. So this would be representing, maybe some sort of live load. Imagine a person standing here. Actually, it says 4,000 pounds. So maybe this is more like a car, right? A car being placed on top of a beam. On this side, this is our weight. And so this would be uniformly distributed. This is imagining the weight of the beam itself. So we're seeing this is rated at 650 pounds per foot. And the way we draw that is a line going across with a bunch of arrows going down, showing that it's uniformly distributed. If it wasn't uniformly distributed, then instead of a flat line, it would follow some sort of a curve or maybe a line, a diagonal line representing a changing weight. All right, next up, free body diagram. You've probably heard this term if you've done a physics class. Really, a free body diagram is isolating all the forces. In this case, we see that our reactionary forces, Fy at A, Fy at B, those are the forces going up. And then since this side was a pin, technically it has a force X coming across. All right, and now using the free body diagram, we'll kind of keep track of all of our forces in the X first. And since we don't have any force balancing out, we can assume that there's no X forces. So that part's going to be easy. Forces in the X equals 0. For the most part, for our class, we're going to ignore all our X forces. We'll only be looking at forces up and down. All right, which leads us to the vertical forces, or forces going up and down. In this case, we're going to assume up is positive just to kind of keep to the convention. So again, we want everything to equal 0. So in order for it to do that, we're going to see that we have a force Y going up, force B going up. Those are the forces of the supports. Next up, we have 4,000 pounds going straight down. That was a point load. And then we have the uniformly distributed load. That's the 650 pounds per foot. And that was happening across the entire beam. So it was 20 feet across. So that's why it's 650 times 20. Now we do some math. 650 times 20 gives us 13,000. Add those together. So in total, our two supports or reactionary forces have to add up to 17,000 pounds. Okay, another way of thinking about it is at A and B, imagine you had two people trying to carry this beam. In total, the beam is 650 pounds per foot, and plus that car sitting on top of it. So in total, we have to support 17,000 pounds. Okay, and so that's kind of showing how we got that. All right, leading next is moments. So moments, remember, is both a force times a distance away. We also want that to equal 0. The part that gets a little bit tricky is the direction now, instead of it being just up and down, is going to be either counterclockwise or clockwise. The typical convention here is counterclockwise means positive. And so again, if we imagine this to be a door and it's hinged at point A over here, if I'm, for example, pushing down on it with point P, that's 4,000 pounds. And again, that's 6 feet away. This would push it this way. Imagine my door would swing down this way, down to the left, which if we think about it in terms of a clock, that would be clockwise. Okay. Meanwhile, our reactionary forces, this force B is pointing up. So if I pushed onto the door, again, imagine we're looking down on the door. If we push on it this way, it would rotate up to the left, which would cause a counterclockwise rotation. All right, so then we start breaking it down. We're going to start from the far right. So I've got force B that's coming this way. It is 20 feet away from the pin. So that would be 20 times force B. There's my moment on that side. Next up, my 4,000 pound force, that's force P coming down. And that is 6 feet away. So that's why it's 4,000 times 6 feet from point A. Finally, we have the 13,000 pounds, and that's 10 feet. Now, the reason how we get that is this 13,000 pounds was the total weight of the beam. We got that from our previous calculation right here, right, 13,000 pounds. And that's going to be 10 feet away because we assume that since it's uniformly distributed, it's going to be applied at the middle of the beam, okay, so or the center of mass, which is 10 feet away from point A. So that's why it's 13,000 times 10. Finally, force A, we're actually comparing it to where the hinge is. Remember, we can't rotate at the hinge itself. And so that's why there's 0 distance from the hinge, hence 0 moment or 0 torque. All right, at this point, we've got our equation set up. We do some math. We see 20 times F, 4,000 times 6 gives me the 24,000, 13,000 times 10, that'll give me the 130,000 pounds, foot-pounds, and then 0. Continue the math here. So this part cancels. We add 4,000 to the 130,000, gives me 154,000 foot-pounds. And finally, to solve for F, Y at point B, we divide the 20. So in total, I see that at point B, this support is going to be responsible for 7,700 pounds. That's what we see right over there. Okay, and now that we know force B or force upwards at point B, we can go back to 2 slides back where we had this equation, Fy at A plus Fy at B needs to equal 17,000 pounds. All right, so putting it all together, we insert that 77,000. Again, solve for force Y at A. That means 17,000 minus 7,700. My final answer for that would be 9,300 pounds. Okay, and kind of just think about this more logically. We see that FA is responsible for more weight than FB. The reason for that, if you kind of think about it this way, remember we had that point force at P, that was 4,000 pounds. Notice it's closer to force A. Again, imagine these are 2 people carrying it. The person A would have to be kind of carrying more weight because it's closer to that side. Okay. And so in total, we kind of just solve for a system of linear equations. So that's the algebra connection there. And that gives me that force A. So this column, or beam, I should say, would be needed to carry 9,300 pounds, while the beam over here at B would be 7,700 pounds. Okay, now this leads us into some graphs. And so first off, these are called shear diagrams. So the shear, remember, is the reactionary forces. And so to kind of imagine what happens with the beam, we would track what's happening to the force as it goes across the beam. So this is force on the y-axis, and then distance along the beam in the x. Right, so to kind of solve this out using the numbers we had, right? Remember we said force at A was 9,300. So it starts off at 9,300 right here. And we see that we have a constant 650 pounds going down. So this is 650 across 6 feet, right? Until it reaches point P. There's my 3,900 pounds. And so we see 9,300 goes down 3,900. Next up, there's a big drop off because that's where point P is. So that'd be 4,000 pounds drop off here. And then we see from the rest here, we have to get all the way down to negative 7,700 on the other side. And so the easiest way would just be draw a nice linear line, because again, that line would be 650 pounds going down every foot. Right, so that's kind of how the shear diagrams work. Okay, so again, we see upward reactionary force upwards minus the applied loads downwards to the left. All right, which leads us to our moment diagram. And so we have our shear, these are our forces. And now our moment diagram, we're going to kind of keep this one fairly simple. It's really, if we get into calculus, I know maybe not many of you guys are in calculus yet, but we would see that this is actually the integral to receive the moment. So you find the area, which allows you to figure out that maximum moment. Okay, so in this case, doing some math here, we're figuring out the moment max. So that's where the little kink in the moment curve is. And to figure out that solution here, we got a little bit more math to do. Let me pause this for a second. Okay, sorry about that, guys. All right, so one more time, what we're doing here is we're figuring out where is the maximum point, and this is kind of where it crosses the x-axis here. So in order to figure out a little bit more about where this point is, I noticed that there is a 1,400 pound gap here, because remember the total on the left side was 9,300. I've got 3,900 on this first section, that 4,000 pound drop off, which led me to 7,900. So there was still 1,400 pounds to get to the total 9,300, which is where it crosses the x-axis. So figuring all that out, this is 1,400 coming down across that 650 pound rate. And so I see that at this point, it's 2.15 feet compared to this little x section. So in total, that means that this point x, where it crosses the x-axis, is at 8.15 feet. And so that's where the maximum moment is. And then I go back to my moment equation from before. I plug in that 8.15 feet value to solve for that here. And again, you can see the math coming through. Put all those numbers into a calculator, and you see your maximum moment would be 45,608 feet-pounds or foot-pounds. All right, I know that was a lot there. Felt like maybe a crazy physics class today, but that's some of the background, especially if you're interested in going to civil engineering or structural engineering. These are the type of the calculations that you should be able to understand. Okay, so there's our kind of a final graph shear diagram and our moment diagram. All right, the one other thing to point out is actually we could have used the graph to figure out the maximum moment as well. This is actually my preferred method. It's a little bit easier in my opinion. So if you figure out the area underneath this curve, so area A would be this triangle. So the triangle would be, about 3,900 pounds high, 6,000 or 6 feet wide. Similarly for B, we can add those numbers together. It's 6 feet across, and then figure out that little area of triangle C. And if we added all that together, you see our number there, we'd get the same value for our maximum moment as what we did with the equation. All right, so I know that was already a lot. Typically, we'd kind of do an example here, give you a chance to try it on your own. I would typically recommend trying this, especially, like I said, if you want to go into civil engineering or structural engineering, then definitely want to spend some time understanding how to do this so you can test yourself, see how this works. But what I will show you guys for your activity today, I will give you guys a couple shortcuts to actually see that your computer, first off, will be able to do a lot of this work for you. In addition, there are some equations that will help you solve this a little bit faster. So next video, we'll go through that, walking through the activity itself. Okay? But if you want to give that a shot, go ahead and do that. And these are kind of the answers for what you should be able to find. The shear is going to be 9,810 pounds on both sides. And then you can figure out the maximum moment should have come up to about 44,145 foot-pounds. All right, so again, I will stop the recording here. The next video will give you more of a rundown of the activity.